Hi everyone, welcome to machine learning using Python. This is the session 18, module 9, part 2 of forecasting. And Jaymeet, our instructor, has been kind enough to continue this series and hopefully part of machine learning study circle. This use case is important and I will hand over to him to go over the slides and explain you all other things. Thank you very much. Jaymeet, take over.
Yeah. So thank you. Thanks a lot, sir. And hi everyone. Let's get started with forecasting. This is part two for forecasting. So before moving to this session, let's just discuss what we did in previous session. In previous session, we discussed what is forecasting and why is it important. Then we discussed about the components of the time series data, seasonal component and stuff. Then we discussed the forecasting techniques, which are moving average and what were the drawbacks of moving average, which was solved by the exponential smoothing. And then we evaluated those moving average and uh, exponential smoothing technique models with root mean square error and mean absolute percentage error. And in the end, we used time series decomposed uh, to be specific seasonal decomposer from the stats model. So continuing this forecasting, in this session, we'll be discussing about the forecasting techniques, which are auto-regressive and auto-regressive integrated moving averages. Then we'll be discussing about uh, ACF and partial ACF, then building the auto-regressive model, forecast and measure their accuracy. Then we'll be discussing about the moving averages processes, the ARMA model, the ARIMA model, and in them we'll be discussing about the stationary data, and to check whether we have stationary data or not, there is something called as Dickey-Fuller test. And then we'll be discussing about the differencing and the forecast and the measuring of the accuracy of those ARMA and ARIMA models. So let's get started. So autoregressive and moving average models are popular models that have frequently been used for the forecasting techniques. We have already used the moving averages in the previous session. In this session, we'll be moving further with the auto regression, which is nothing but a regression technique on the variable of itself. So we are predicting the variable's value with variable's past value. If mathematically speaking, the autoregressive with lag 1 or AR1 will be represented with yt plus 1 equals to mu plus beta yt plus epsilon t plus 1. And in general, with AR model of P with P lags, it can be represented by the yt plus 1 minus mu equals to beta into yt minus mu plus epsilon t plus 1, where epsilon t plus 1 is nothing but the residuals. And here we are assuming that the sequence of uncorrelated residuals, which is represented by epsilon, to follow the normal distribution with zero mean and constant standard deviation. And yt minus mu can be interpreted as a deviation from mean, and it is also known as mean centered series. So we already know that we are uh, working with auto-regressive models, auto-regressive models. But one of the important tasks with AR models is identification of the number of lags value. So for those for identifying those number of lags, we have two approaches, which is auto correlation function and partial auto correlation function, ACF and PACF respectively. So starting with the auto correlation function ACF, for lag k between yt and yt minus k can be measured with at different k values, and we can also use auto correlation graphs or plots which is called as correlogram. So that we'll be using with stat models, graphics, TSA plots, and plot ACF. And the same goes for partial autocorrelation function for the plotting, but it's for PACF plots. Here, the partial autocorrelation for lag k or lag value k is a correlation between yt and yt minus k when the influence of all the intermediate values, which y, yt minus 1, yt minus 2, yt minus 3, and so on till yt minus k plus 1 is removed from both yt and yt minus k. We'll both be understanding this using the plots called correlogram, and we'll be using stat model for both ACF and PCF plots. So we'll be understanding this with the help of an example where let's read out the example. So aircraft spare parts monthly demand for avionics system spares used in Viman 007 aircraft is provided in the file. So we'll be building an ARMA model based on the first 30 months of data and forecast. The demand for spare for month 31 to 37. So when we read this CSV file, you can see that we have month and demand as the index, as the columns, and you can see the first few records of those months. And the information regarding the data set, which reveals that we have 37 entries, and all of them take integer data type and two columns. So this is what we were talking about when we are talking about correlogram. This is correlogram for ACF. So we built this correlogram, and you can see the plots, and also there is a background of blue. So uh, in the shaded area represents the upper and the lower bounds for the critical values where the null hypothesis cannot be rejected. So the autocorrelation value is 0, and you can see that the null hypothesis is rejected only for lag equals to 1. So so that it means that the autocorrelation value over here is statistically significant for lag equals to 1. And now we'll be drawing the PACF graph for the same, and it's showing the same thing, that the apart from the lag value 1 is significant for us, and yeah, so this will be easier to understand. So the so As mentioned, that shaded area represents the upper and lower bounds of the critical values where the null hypothesis cannot be rejected. So for the first, which is autocorrelation function, ACF, the null hypothesis is rejected only for lag equals to 1. And for PACF, the partial autocorrelation, the lag equals to 1 is significant. So we'll be moving further with a lag value of 1. So when building an AR model, uh, we can use these rules to go further, which is for partial autocorrelation is significant for first p values and cuts off to 0, and the ACF decreases exponentially, which are the signs of stationarity. So for our case, the ACF and PCF plots, the lag value is 1. So we'll be moving further with AR1. We'll be using the stats model, TSA ARIMA model to build, which takes two parameters, which is endog or endogenous values and the order. In order, it takes P, D, and Q, where the order is given by value of P, order of integration is given by D, and order of MA is given by Q. So, but we'll be only using the P values here for. So, when we build this ARIMA model, and fit it with the data and get the summary for it, you can see that in the second part of the summary, which starts with coefficient, standard error and stuff, you can see that the p value, p greater than mod t, we are getting the value of 0.0056. So the model summary indicates that AR with lag 1 is significant variables in the model, and the corresponding p-value is less than 0.056. Next, we measure the accuracy of it. You can see the function get MAPE, which is mean absolute percentage error that we built in the previous session. So this is for the reference of that we'll be using this to measure the model as well. So when we use this to measure the model for our 31st to 37th value in the data set, you can see the values that we get for the predictions, and using the getMAPE function, we get the MAPE value for MAPE value for 19.12% for our AR model with lag 1. So the moving averages are a regression model in which the past residuals are used for forecasting future values of the time series data. So as we are going with lag value 1, so our MA can be represented as YT plus 1 equals to alpha 1 epsilon T plus epsilon T plus 1. Please ignore the plus sign before the alpha. It is a typographical error. So the model in equation can be generalized to Q lags, which here the Q denotes the number of lags. So in moving average process can be identified using the following rules, which is autocorrelation value is significant for first Q lags and cuts off to 0, and the PACF, the partial autocorrelation function decreases exponentially. So just just a second. So when we build this moving average model and give it the value of q equals to 1, which is for the number of lags, and get the MAPE, or the mean absolute percentage error for this, we get the value of 17.78, or 17.8. Now moving further with the auto regressive moving average, or ARMA, which is combination of both the auto regressive as well as the moving average process. So ARMA takes P and Q. ARMA PQ process combines both the autoregressive P and the moving average Q processes. So for identification of values of P and Q in the ARMA process, it can be identified using the two rules, which is first one is autocorrelation values are significant for first Q values and cuts off to 0, and the partial autocorrelation values are significant for first P values and cuts off to 0. So in the uh, ARIMA model, the the ARMA models are used only when the time series data are stationary, but ARIMA models are used when they are not stationary. So sorry. So the time series data is called stationary if the mean, variance, and covariance are constant over the time. So we'll be using the ARIMA and the parameters which are PDQ, where P is represented by the P lag, number of lags, D with the integration component, and MA with the number of Q lags. Remember, the P value is for AR component with P lags. So the main objective of the integration component is to convert a stationary time series to a non-stationary time series to a stationary time series, because we are using the ARIMA model, and ARIMA models use a non-stationary time series data. So when the data is non-stationary, the ACF will not cut off to 0 quickly, and rather ACF will show a very slow decline. So what is stationary data first? So the mean value of YT at different values of T are constant. The variance of the YT at different time periods are constant. Or we can say that it is homoscedasticity, where homoscedasticity is nothing but the term for constant variance. And the covariance YT and of YT minus K for different lags depends only on K and not on time T. So for this, we'll be uh, taking another data set, which is store.xls. Here we have the daily demand for a product in a store for the past 115 days. And we have to develop an ARIMA model that can be used for forecasting the demand of an omelette. So first we read the data set. You can see that on the snapshot on the right, that we first read the data set and display the first few values, and you can see that we have date and demand, two columns. In the info, after getting the using the info method, we get to know that there are 115 total entries, two columns. The date takes the date time data type, whereas the demand takes the integer data type. So as we want to be aligned with usage of this date. So basically what we are doing over here with set index and dropping the date is that we are creating a date time index, which will make sure that the data is ordered by the date or time. So after making the changes and dropping the date, we display the last 5 records in order to see that whether it has sorted using the dates or not, and you can see that it has. When we plot the graph for ARIMA model on date and demand, you can see that there are certain patterns we can see, but we cannot say it for sure that it is a trend for the stationary data or not. When we plot the ACF plot, it's gradually decreasing, or it shows a slow decline for auto correlations for different lags, indicating that the series is not stationary. So as you remember in the very start that I mentioned about the Dickey-Fuller test, which is for checking whether the time series is stationary or not. So remember the equation yt plus 1 equals to mu plus beta yt plus epsilon t plus 1. Here it checks whether it is equal to or less than or equal to 1. So the hypothesis testing is done. For the null hypothesis, which is represented by H0, the beta value is equals to 1. And for alternate hypothesis, our beta value is smaller than 1, which means that the time series is stationary. And if the p-value is less than 0.05, the time series is stationary. So for this Dickey-Fuller test, we'll be defining the a function called add-Fuller test, which will take TS as a parameter. Then using that function, we get the test statistic p-value and lags used. And you can see that it's 0.46, which is greater than 0.05, which indicates that we cannot reject the null hypothesis, and hence the series is not stationary. So as a series is not stationary, we'll be using differencing. So the first difference between the values of yt can be computed by subtracting the previous day's demand. So the shift function that we have used from pandas in the previous one, we can use this shift function again to subtract with the previous values. So as we are starting with the first rate will not be having any previous values at as we do not have any uh, values for a day before that for index 0. So it will have a nan value, but after that you can see that we have the demand difference, which is nothing but a new column that is added for storing the differences. When we plot the graph for the date and the first order differences, it indicates that the trends of first order differences over the demand over dates, and it is not very apparent from the trend if the series is stationary or not. So we'll be using the ACF plot again to verify whether it's stationary or not. So you can see how the autocorrelation function shows and the plot shows for it. So it shows no sign of a slow reduction in autocorrelation over the lags, and it immediately cuts off to 0. So we can build a model for the first 100 observations for training set and the subsequent observations for the test set. Just a second. So just a second, let me just get back at. So remember that we made the demand difference and made the plot over here. So, and later on we tried to check it with the ACF plot in order to know the stationary, whether the data is stationary or not. And the trend is because from the graph that was plotted here, it was not very apparent that if the series is stationary or not. And because of that, and from the ACF function also, it was not very apparent. So that's why we used 100 observations as the training set and the subsequent observations as as the test set, and getting the and using the ARIMA model and getting the summary for it. So the RIMA model uh, has to satisfy all the assumptions of the regression model and or the regression. So the residuals should be white noise and not correlated. This can be observed by using the ACF and PACF plots for the residuals. So the model residuals are given by the ARIMA model residual variable. You can see the autocorrelation graph and the partial autocorrelation graph for the both. Now measuring the accuracy for it. So here we'll be using the forecast method, which takes the number of future periods or stats for predicting values and returns the predicted values along with standard error and the confidence interval for the predictions. So store, predict, standard error and the confidence interval is unpacked for the 15 steps. And when we predict and we print those values, you can see that we get the array of the values. And when we get the use the get MAPE in order to measure the accuracy of the model, we get the uh, differencing the first order differencing giving the forecast accuracy of 24.17. So this was the graph for the ACF plot and the PACF plot that was created lastly for the ARIMA model that we just discussed. And for forecast and the measuring of the accuracy, if the way it shows over here and it shows any kind of error, you can unpack these values individually. So just in case you do not, you can get work with. And then store predict, and you can see that we are getting these value for the predictions. And for those predictions of the ARIMA model, we got the accuracy of 24.17%. So to summarize today's session, we started our discussion with the auto regressive model, then auto regressive integrated moving averages, which is called ARIMA. And then we discussed about the ACF and partial ACF, which are used for the values of P or the number of lags that we can get. And using those ACF and PCF value, we got the value of 1 for our while building our first AR model. And we checked the AR model with the get MAPE method that we have built. And after checking those, we discussed with the moving averages process for ARMA model and the ARIMA model. And we started its discussion with the help with understanding what is stationary data, then knowing to check whether we have a stationary series or not. We used a Dickey-Fuller test for which we individually made a function called add-Fuller, use differentiating, and specifically using the shift method from pandas in order to get the difference for the current and the previous value, and forecasted the ARIMA model or predicted using the ARIMA model. Though we are using the forecasting technique, I'll be sticking to the word forecast. So forecasted the values of the ARIMA model and measured the accuracy, for which we got 24.17%. So this is it for the session on forecasting. These are the only references that I have for forecasting and time series, which are for the whole module of forecasting. So yeah, this is it from my side. Thank you.
Yeah, Jaymeet, well
Yeah.
done
Yeah.
for presenting. It was a what you call a little bit more technical than people would have expected, but that's okay. Let them learn.
Yeah.
And additionally, what I would say, did you have any references of forecasting which we had done previously from the book, some other book last year or last to last year, I don't remember. Okay.
Forecast. If I have it, I will share it. But these are the ones only that were
If
used.
you want to add that to these references, just in case you have it, just add it. That book which was there,
Okay.
we just add that so that forecasting is not just theory, it is also practice and it
Yeah.
is practically used, right?
Yeah.
Make sure that practical portion of it where it is used is reflected here. So at least you can leave the link for that book and say which chapter covers that. Okay.
Okay. Okay.
So I think that is all.
Yeah.
And I think I will end the call with this. So
Sure.
are we, one second, let me stop first.